Hello, welcome back. Up until now, our input and output has always been communication with the user through the console. And it's very useful to be able to write data into disk files and read the data back from the files, so you have persistence of the data. And that's what we're going to look at in this segment. It's not too difficult. You could probably figure this out on your own, but there are some pitfalls that can cost you a lot of time. So why don't I just show you how to do it, and it'll make the learning of it a lot faster. So let's have a look now at the functions that we will use to read and write files in C. So let's start out by thinking about what a file is on the disk. And I want you to think of a file simply as an array of bytes on the disk. So you know a file has a name and it has a location on the disk, but think of it other than that as just an array of bytes starting with the 0th byte and going to a special byte which is called the EOF marker, or the end of file marker. When you read and write into a file, you use a file position pointer or a file pointer, and as you read from the file, this pointer moves along the bytes as you read them, or as you write into the file, the pointer moves along so that you don't write over what you just wrote. So it works kind of the way that you would expect it to. When you are writing into a file, you take data from your variables and you place them in the file, starting at the current location of that file position pointer. And conversely, when you read them, you read from the position of the pointer, and the pointer moves along as you read things out of the file. The end of file marker is a special character, and it's put there by the operating system, and the functions that read and write the file can check for this end of file marker so you don't read past the end of the array of bytes that represents the file. There are two kinds of files that we're going to talk about, the text files and binary files. So text files are simply a sequence of bytes on the disk where each byte represents the ASCII code for some character. And each character is 1 byte large, which is the same as a char variable in C, or char. Text files usually have an extension txt so that they can be easily recognized by programs that can read text files. For example, if you double-click on a txt file, you usually have Notepad pop up, and it reads the bytes out of the file and displays the characters in the Notepad editor. So inside of the txt file, you can have special characters other than the printable characters that represent the letters and numbers and punctuation and spaces and so on. For example, the end of line character, it can be 1 or 2 characters depending on the operating system. So a carriage return and a line feed, or \n and \r, are what would end a row of characters as displayed by Notepad or some other program that can read a text file. And the end of file character, which is in Microsoft Windows, for example, this is the numeric hex 1A. So that's the actual numbers that go into the file to indicate that that byte is the last byte in the file. You as the C programmer don't really have to be concerned about what that actual numeric is. The functions that you use to read the file will recognize that it's come to the end of the file. So that's how a text file works. You put ASCII codes of characters into a file, and that's what is represented in the bytes. Binary files are quite different. They are a sequence of bytes in the file, and they represent raw data. So, for example, if you write a double into a binary file, 8 bytes of space that take up the double are the 8 bytes that actually go into the file. So those wouldn't represent a printable character like the ASCII code of a number or of a printable numeral. Those actually are the 8 bytes of raw data that represent the double value. You can't open a binary file in Notepad and look at it because they're not ASCII characters. And in a lot of ways it's easier to read and write binary files because there's no issue of formatting the text on the lines. So for example, all of the issues that you've had with printf statements, getting the characters to come out on the console in the right position, those same issues come up with reading and writing text files, but they don't come up when you read and write binary files. There's no concept of putting space on the line or space characters so that things come out in the right place. When you view them, the binary files are not meant to be viewed. They're meant to be read by other programs. So let's start looking at the things that you have available to work with binary files. We've been using standard io.h to have access to printf and scanf, and that H file also gives us access to the things that we need to read and write files. So we are introducing now a new data type that's defined for you. It's the file pointer, and that's in all uppercase, and it's used to have your C program connect to a disk file. And here's how you declare one: a file pointer input file, and of course the space, the asterisk can go next to the file or next to the variable name. It doesn't make any difference. And to make the connection to the file, we're going to call this function fopen. It stands for file open. And then the first parameter is to specify where the file is. So if we want to open a text file called mytextfile.txt, and it's on our C drive at the root directory, we would write it this way, and then the second parameter of fopen is the mode that we want to open the file. So for example, if we put a lowercase w there, that means that we want to write into this text file that we're opening. Notice the 2 slashes here. Remember that if you put a backslash inside of double quotes, it means that the next character is something special. So on this path that we're specifying to the file, we want to use a backslash, and we can't unless we put 2 of them. So the first one indicates that the next one represents a slash in this string. Okay, so fopen will return for you a pointer to that file, and I've stored it in the variable input file. When you're done writing stuff into this file, you call the function fclose and pass in the pointer, and it disconnects your program from the file. This is kind of important. We should remember to close the files that we've opened. Okay, so what are all of the possible modes that you can fopen a file? If you're opening text files, you use one of these modes, and if you're opening binary files, you're going to use one of these modes. And these are the possible combinations. If you open the file for a text file for reading, you're going to use R or W if you're going to write, or A if you want to append things to the end of an existing file. So these are the modes that you have to use when you're opening a file for reading or writing. Let's look into this a little bit more. We're going to look at how we would do input and output for text files. So this is what we had already. We did an fopen of the file for writing, and it gives us back a file pointer. If this fopen function call failed for some reason, it will return null, which is a numeric 0, and we should probably check and see if it failed to open that file. So you might not have write access to the place where you're trying to place the file, so that fopen would fail. Or if you're opening it for reading and it's not there, then the fopen would fail to return a valid pointer. If you're opening a file for writing and it isn't there, it will be created for you. So if we have no file on the C drive called mytextfile.txt and we open it for writing, we will make a file in that directory. So you should really check and make sure that you did make a connection to a file. And now you're used to printf function for putting things out on the console. There's a similar function called fprintf, and the first parameter is a file pointer, and the rest of it works the same way. So with this code, we would open a text file and then write into it a string, put this in the file, and the number 123. So you're used to this in a printf, and the only difference with an fprintf is that you specify the file that you're going to write in, as opposed to the printf just dumps things out onto the console, and then we'll close the file. So printf and scanf have corresponding fprintf and fscanf functions that work pretty much the same way. So in this example, if we want to read from a text file, we do the same thing, make a connection to the file by using fopen, except that we're going to use the mode R for reading the file, check to make sure that it did open correctly, and then scan something out of the file. So if we try to read the file that we just wrote, there's a problem. And this is one of the reasons why text file input and output is tricky. So if you remember from the last slide, we wrote a message and a number. So that seems to mean that we should be able to read back a character array as a string and a number. And it won't work because %s is fairly complicated. It will stop reading characters out of the file the first time it comes to a white space. So that might be end of line, or it might be a space. And in our message we had spaces, and then the %d will not match the following characters. So this one won't work. It's a little bit tricky, this %s thing. You have to read the specification for exactly what characters %s will eat up out of the file as it moves the file pointer along inside the file. So that's the pitfall with fscanf. Here was the printf, and when we do an fscanf, I said this wouldn't work because this %s would read put and then stop when it comes to the first space. And then the %d will not match these characters because that's not an integer value. So %s can be modified in various ways, or we could use another format specifier like this % and something inside of square brackets. So what goes in there? You can specify things that you want to include. So this is characters that you want to eat up out of the file without stopping. For example, I've specified here I want to read all of the lowercase characters A through Z and a space and all of the uppercase characters. So this would stop when it comes to any digit. Or you can specify anything that you don't want. So in this case, the hat indicates that I want to read all of the characters in the file until it comes to a semicolon. So you'll be reading characters out of the text file until it comes to something that you don't want. And that's what the little hat means inside of the square brackets. And what goes inside of the square brackets, it can be fairly complicated. You have to Google around and find out the exact specification. I'm not giving you all of the combinations of things that can go in there for this introductory kind of lesson for reading and writing files. There are a few other functions that are available to you for reading and writing text files. You don't have to use these. You want to do everything with fprintf and fscanf, you can. These are a little bit more convenient in some cases. So the first ones we'll look at, fgetC and fputC. This reads one character out of the file, and this puts one character into a file. And this odd one, ungetC, if you read a character that you didn't want, you can stuff it back into the file to be read later. fgetS and fputS are used to write out a line from the file, and sometimes it's easier to read and write entire lines at a time, given the issues that were raised in the previous slides using the %s format specifier in fprintf. And feof is a function that finds out if you're at the end of file, and it will return true or false depending on whether you're attempting to read past the end of the file. So let's look at these two lines of code down here. This is an entire file copy, one character at a time, for use with text files. So fgetC returns either one character from the file and puts it into this variable ch, or it will return the EOF marker. So we read the character out of the file, and this assignment statement evaluates to whatever went across the assignment. We compare that. If it's not end of file, then we put the character that we read into the output file. So this loop, 2 lines of code, will read all of the characters from one file and put them into another file. I didn't show you the declarations of these, but these are simple file pointers that were declared, and a file associated with those had to have been fopened. So let's change gears now and start looking at binary file I/O. And the file pointers are the same, and the fopen is the same, except for the mode that the file is opened in. And we're going to use different functions for doing the reading and writing. So we have 2 functions called fread and fwrite. Some people call these freed and frite. And you can use these to pretty much achieve all of the binary file I/O that you have. There are some other functions that make things easier and more efficient, but these are the 2 that are the most important. So let's look at fwrite first. Fwrite takes 4 arguments. The first one is the address of the data that you're going to write into the file. So that's one number, an address of the starting place of the data that will be written into the file. And then if that pointer were an array, we would specify the size of each element going into the file and the number of elements, and the last argument is the file pointer to specify what file we're using for this fwrite. So let's look at a very simple example. Declare a double variable and put a value in it. So there's 8 bytes of space with 27.5 in it, and we want to write that value into the file. So here's the call to fwrite that would achieve that. Give it the address of the data that we're going to put into the file, and then the size of how many bytes of space. How many are there? Well, there's only 1 this time, and the file pointer is the last argument. So that would write, that one fwrite statement would write 8 bytes into your file. Those 8 bytes would have the value in at 27.5. Let's look at another example where we have an array that we want to write into the file. So here's the fwrite. Remember that the name of an array already has the address of the first element in the array, so we don't put an ampersand there. We're specifying a pointer to the data, which is in the name of the array. And then the second argument is the size of each element in the array. The third argument is how many there are, and the last argument is the file pointer. You can also use fread and fwrite to read and write data structures, or structs, that you've created into a file. So remember in previous segments we had created a new struct called date, and we use a type def, so we just have date in all uppercase. And here's the declaration of one of those things. If we want to write this data structure into the file, give it the address, how many bytes there are. In this case there's only 1, and the file pointer. And then when you read them back, you might expect that it works exactly the same way. You give in an fread, you specify where the data is going to land when it comes out of the file, and how many bytes there are, how many of them there are, and the file you're reading out of. Using binary files, it's possible to move the file position around. So we have this file position. When you first open the file, it points at the 0th byte in the file. If you want to jump from place to place in the file, we have some functions that allow you to do that. If you're not jumping around in the file, you're said to be doing sequential file access. So if you read the first bytes and then the next bytes and then the next bytes in sequence all the way through the file, then this is sequential file access. If you want to jump around in the file and do random access, then we have these functions available. So fseek will move the file position to a specific place in the file, and you can seek to a specific byte in the file. You can ask what position are you at, get the file position pointer, and you can set the position pointer. This is another one that asks what position are you at, ftell, and this one is kind of a throwback. You can rewind. If you rewind the file, that kind of makes you think that it's like rewinding a tape, and that's where that name comes from. But rewinding a file puts the file position pointer back to 0, and you can start reading from 0 again. I'm not going to go through the details of each of these, but it is possible, quite possible, to write and read from random places within the file. Okay, let's have a brief summary of what we've covered in this segment. Think of files on the disk as a sequence of bytes, and it doesn't matter whether you're thinking about a text file or a binary file. They're just bytes on the disk, and there's a special byte at the end that indicates that the file is over. If you think of it almost like an array on disk, then it's easier for you to think about what your functions are doing that are reading and writing from the file. So we looked at both text files, where the ASCII code of characters is stored in the file, and binary files, where raw data is stored in the file. Reading text files, everyone is tempted to use text input and output all the time because you can see what's going on more easily than with reading and writing binary files. But reading text files is really very difficult, and the format specifiers, you have to know exactly what the format specifiers are doing so that you'll know which characters get gobbled up out of the file and put into your RAM variables. If you can do your input and output in binary files, it almost always is easier in the long run. You just have to be very careful that you know exactly what bytes are getting written into the file, and then when you read them back, you'll have the right data types in the right variables. So it is impossible to read a binary file without knowing what the bytes represent in the file. I suppose that you could say you can read one byte at a time and treat all of the bytes in the file just as a byte. And sometimes that's what you would have to do. If you don't know the format of the data, you have to read the bytes one at a time and see if you can't figure it out. But it's a very difficult process. So you really need to know the file format. What do those bytes represent? Are they ints or doubles, and in what order in the file, so that you can correctly interpret the data that you're reading from the binary file. Binary files are easier to work with in a lot of ways. You can read and write large blocks of data at a time. So if you have an array of structs, for example, you can put all of that data into the file using one fwrite function, and you can read them back using one fread. So it is easier to get around in binary files once you get the hang of it. And this one is kind of unfortunate. You can mix the reading and writing of files between text and binary formats. So that means you can open a file for reading binary and then you can use the fscanf function, but it almost never works. And it's very, very frustrating. And I watch students try over and over to change their function calls and their format specifiers to try and make something work, and it looks promising and you can almost get it to work, and then getting the last little bit of it to work. So just don't do that. Don't mix binary and text file function calls. If you're opening for a file for text input and output, then only use the fprintf, fscanf, the functions that are intended to be used for text input and output, and vice versa. If you're using a binary file, then only use the functions that are working with reading bytes and writing bytes in and out of the binary file. Okay, reading and writing files is a lot of fun. It's powerful. You can do stuff with it, and it makes your applications, your C programs, a lot more interesting. I'll see you in the next segment.